Welcome to part 2 of chapter 13. And again, I'm splitting these videos into 2 parts or maybe even 3 parts to lessen the load I'm burdening YouTube with, and also to give you a chance to look at smaller bite sizes for looking at the lectures rather than having to sit through 2.5 hours in one sitting. So with part 2, we're going to continue on with our discussion of integer linear programming, and we're at the point now where we're looking at how binary variables can help us consider fixed costs in our optimization models. So a fixed cost problem uses binary variables to indicate if an action is taken and it has a fixed cost, then that fixed cost will be applied. If not, it won't. And so this is a perfect opportunity for using a binary variable. We set it to 1 if the action is undertaken, or if it's not, we set it to 0. So let's take a look at this in action in the RMC example. So here's the spreadsheet for RMC, and we'll go over the case history. The production problem faced by RMC is they have 3 raw materials that are used to produce 3 products: a fuel additive, a solvent base, and a carpet cleaning fluid. So the decision variables are the tons of fuel additive produced, the tons of solvent base produced, and the tons of carpet cleaning fluid produced. And these decision variables are represented in the vector B21 through D21 under fuel, solvent, and cleaning, respectively. However, there's a fixed cost for setting up. It's called the setup cost for each one, and we see those setup costs here under the setup cost, and that vector is B10 through D400. Now, we represent those possibilities for the setup costs here. One indicating there is a setup cost, so in other words, we're going to make some of the particular product, or a 0 if we're not. So if we go ahead and change this to 0 here, then that means we have a 0 for our setup cost. We also have profit contributions, and it's $40 per ton for fuel additive, $30 per ton for solvent base, and then $50 per ton for carpet cleaning fluid. And that's in this particular vector here. Each ton of solvent requires 0.5 tons of material 1, 0.2 tons of material 2, and 0.3 tons of material 3. Each ton of fuel additive requires 0.4 and 0.6 of materials 1 and 3 respectively, and likewise for cleaning fluid. The total tons available for material 1 are 20, material 2 5, and material 3 21. So we also have capacity limits of 50, 25, and 40 tons for producing the various products. Here you see the net profit is going to be equal to the cost of, or the profit per ton that we make times the quantity that we make for each one of the items. So that's going to be the multiplication of the vectors B9 through D9 and B21 through D21, and we do a sum product on that, minus the sum product on B10 to D10, which is going to be the setup cost, times D22 to B22 to D22, which is where we indicate if we are going to use the product or not, in which case we put a 1 and therefore there would be a setup cost. If not, we put a 0, and 0 times the setup cost would still be 0. So now we've got our model set up, and we can use this binary variable to represent setup cost. So we're looking at the RMC data that's available concerning the setup cost and maximum production quantity for each of the 3 products. The modeling flexibility provided by binary variables can now be used to incorporate the fixed setup cost into the production model, as we've just gone over. And again, the setup cost for each one of the products, fuel additive, solvent base, and carpet cleaning, are in our model. So let's take a look at what this is, how this translates into our solver. Okay, and let me move this. Well, I'll move it around. So our objective is going to be C17, the maximum net profit. We're going to do that by changing the variable cells B21 to D22. And that's this particular list in our Excel table. B22 to D22, that's the setup indicators, are binary. In other words, they can be 0 or 1. We also have the constraints that G18 through G20, the amount of material used for each one of the materials, is less than the available tons for each material, and likewise that the tons produced is less than the capacity of tons that we can produce, which is G23 to G25 is less than H23 to H25. So we can go ahead and solve this one. And we see that we maximize our net profit, and that's going to be this 1,350,000 by producing 25 tons of fuel additive, 20 tons of solvent, and 0 tons of cleaning. And notice that we have a 0 in for the setup indicator, and therefore we do not incur any of the $400,000 setup costs for that. And we have some slack in our solvent, and likewise in terms of materials and in maximum capacity. Okay, let's go on with the next item. So we're going to review Salem Food Company, and so we'll pull up their worksheet, and this is an example of what's known as conjoint analysis, and that's a market research technique that can be used to learn how prospective buyers of a product value the product's attributes. So product design and market share optimization problems are sometimes they're called the share of choice problem, the choice of a product design that maximizes the number of consumers preferring it. So we have various factors in our product, and these factors have a certain amount of appeal or utility to our customers. And what we want to do is we want to maximize the interest of our customers or the utility of the product for our customers by rearranging the various choices we have for product features. And we can illustrate that with a pizza company where they've got the ability to make a thick crust or a thin crust. They can, for cheese, use a blend or a mozzarella. For their sauce, it can be smooth or chunky. And the sausage can be mild, medium, and hot. And so with our consumer, we can look at what their utility is for each of these various features and come up with also a comparison of those to their current favorite pizza to see if we can rearrange the characteristics of our pizza so that it's better than the characteristics of their current favorite pizza. So what we want to do is we want to maximize the choices here to be greater than 52 for customer 1, 83 for customer 4, and so on. So this is a product design and market share optimization problem. The results of conjoint analysis can be used in an integer programming model of a product design and market share optimization. A part worth is the utility value that a customer attaches to each level of an attribute. So, the background is Salem Foods is planning to enter the frozen pizza market. And there's two existing brands currently, Antonio's and King's. And they have the major share of the market. So what Salem Foods needs to do is try to develop a sausage pizza that will capture a substantial share of the market. And Salem's determined that the four most important attributes when consumers purchase a frozen sausage pizza are crust, cheese, sauce, and sausage flavor, which we see reflected in our model. The crust can be thick or thin, cheese, mozzarella, or blend, and so on for the other characteristics. In a typical conjoint analysis, a sample of consumers is asked to express their preference for a product with chosen levels for the attributes. Then regression analysis is used to determine the part worth for each of the product attributes. The part worths can be used to determine the overall value or utility that each consumer attaches to a particular type of pizza. In general, each consumer's utility for a particular type of pizza is the sum of the part worths for the attributes of that type of pizza. So what we have in this particular chart are the different levels of each attribute provided by a sample of 8 potential Salem customers who are currently buying either King's or Antonio's pizza. We have the provided part worths, for example, 11, 2, 6, 7, and so on, from aggression analysis, and we'll then use those to provide an overall value a consumer attaches to a particular configuration, if you will, of our pizza. So for customer 1, the part worths for Antonio's brand pizza are 2 for thick crust, 6 for mozzarella, 17 for chunky sauce, and 27 for the flavored blend, medium flavored sausage. And so customer one's utility is 2 plus 6 plus 17 plus 27, or 52. On the other hand, for customer one, the part worths for the King's brand pizza are 11 for thin crust, 7 for cheese blend, 3 for smooth sauce, and 26 for the mild flavored sausage. So customer one's utility for the King's brand pizza is 11 plus 7 plus 3 plus 26 equals 27. So Salem has to design a pizza, in other words, choose the type of crust, cheese, sauce, and sausage flavor that will have the highest utility for a sufficient number of people to ensure sufficient sales to justify making the product. So assuming a sample of 8 consumers is representative of the marketplace, we want to formulate and solve an integer programming model that can help Salem come up with a design for their pizza. And in marketing research literature, the problem being solved is the share of choice problem. So the decision variables are 1 if Salem chooses level I for attribute J and a 0 otherwise. And we can see this reflected in our model here. So here we've got a particular configuration, and so here we're choosing 1 for, in this case, crust and thin. So that means that thick has to be a 0. And likewise for cheese, we're choosing 1 for the blend and 0 for mozzarella. For the other variables, the same thing. 1 for mild, medium, and hot. And then we can look at maximum share is going to be the sum of H22 through H29. So H22 is here, and it's, are we going to capture this particular consumer? And if we do, then we give it a 1. If not, for example, in this particular configuration, we do not capture consumer 3, then we give it a 0. So that's how we're going to set this one up. So let's take a look at our data solver for this one. So what we want to do is maximize our market share. In other words, how many of our customers that we are sampling, or rather potential consumers that we're sampling, would prefer our combination of features over either Antonio's or King's brand pizzas. So we're going to maximize that, and we're going to do this by changing the configurations of B16 through J16. And also, we're going to look at, are we changing H22 through H29. Now, these sets of variables are binary. They can only be a 0 and a 1. We also have constraints that C22 through C29 are greater than E22 through E29. So let's take a look at these variables, C22 through C29. And these are going to be the multiplication or the sum product of B5 here. Well, let me come back to this one. B5 through J5. So here, back to there, times B16 through J16 here. So whether or not we select a particular characteristic for our product. And if we do, then we get the part worths for each one of them multiplied by the 1. If we don't, then the part worth is multiplied by 0 and it doesn't have any effect. So what we want to do is we want to find out, okay, is this particular combination right here greater than the current favorite? So we take minus K5, so we're going to get the sum product right here, and if this is this sum product of the features is greater than the current favorite, then we're going to have a positive value. If it isn't, then we're going to have a negative value. So we want it to have at least greater than 1 positive value. So in here we will make sure we've got that constraint. C22 to C29 is greater than the E22 to E29. We just want it to be positive 1. And if we don't capture a particular customer, then what we're subtracting, we're multiplying our favorite K5 factor by 0. So we won't end up with a negative value there. Then we also want C32 to C35. Let's go down a little bit. To equal E32 through E35. So that we've chosen a crust, a cheese, a sauce, and a sausage. So we have to select one for each of them. We can't say, well, we're not going to have a sauce on our pizza, or we're not going to have a sausage on our pizza. We've got to have all 4 of those items. That's what that constraint indicates. So let's go ahead and solve this and see what our maximum potential customer share is going to be. And so this is what we get when we run it. And it turns out that we pick up 4 of the 8 in this particular case. So that's something that management can look at and decide they've got a chance of picking up 50% of the customers with this particular option. Thin crust, a cheese blend, chunky sauce, and mild sausage, based on these preferences indicated by consumers for what they like in terms of thick and thin, mozzarella, and a blend, and so on. Okay, and of course, we've gone through this. Here's the part worths for the Salem food problem. And here's our equations. If we want it to be greater than at least one more. So in other words, we don't want it to be as good as the pizza that they like the best. We want it to be better. So we have to add 1 to the factors they give their current favorite in the rating. Okay, so let's see some other flexibility that we can get with binary variables. So binary variables can also be used for multiple choice or mutually exclusive constraints. Also in situations where we want to choose k projects out of n projects that are possible for us to invest in, or situations in which the acceptance of one project is conditional on the acceptance of another project. So let's see how we can do that by adding constraints into our solver model. So a multiple choice constraint is a constraint requiring that the sum of 2 or more binary variables is equal to the value 1. And any feasible solution that makes a choice of which variable to set equal to 1. So in other words, we're giving them a multiple choice, let's say A through D, and they can only choose one. So of those 4 variables, one of them is going to have the value 1, the others will have the value 0, and then the sum of them will be equal to 1. That's the multiple choice constraint. We can also do the mutually exclusive constraint, and that's a constraint requiring that the sum of 2 or more binary variables be less than or equal to 1. So if the variables are equal to, if one of the variables is equal to 1, the other is equal to 0. On the other hand, all variables could be 0. So if you'll think back to our ice-cold refrigerator example, we had the option of a warehouse expansion, and we had 3 warehouse expansions. We had the original warehouse expansion project, the second warehouse expansion project, and the third warehouse expansion project. So this was a multiple choice constraint that we might want to put into that. So we'd say for W1, 1, it takes on the value 1 if the original warehouse expansion project is accepted, and 0 if it's rejected. 1 if the second warehouse expansion project is accepted, and 0 if it's rejected. And then same thing with the third warehouse expansion project. 1 if it's accepted, and 0 if it's rejected. And then the multiple choice constraint reflecting that requirement would be W1 plus W2 plus W3 equals 1. So what that's telling solver is if it sets one of these to 1, the other 2 have to be 0. So that way we can only select one of these projects. So that's how we add in a multiple choice constraint. So we can also add in a multiple choice constraint where the one warehouse must be expanded if that requirement is that the warehouse must be expanded did not exist, then the multiple choice constraint could be modified so that W1 plus W2 plus W3 is less than or equal to 1. And that will give us the opportunity to not do any of the warehouse expansion projects. So in other words, they could all three equal 0. It still does not permit more than one warehouse to be expanded. So this is a mutually exclusive constraint. So that's how we would add in the mutually exclusive constraint. We add the less than or equals relation operator. Another thing we might want to do is the k out of n alternatives. So let's say we had 5 projects that we could invest in, but we only wanted to do 2 projects. So only 2 of the 5 projects would be accepted. So the way we would satisfy this constraint is we would make the binary variables W1, W2, 3, 4, 5 equal 0, 1, obviously because they're binary, and this sum of W1, W2, 3, 4, and 5 is equal to 2. That way, the most they could do is 2. Now, if k was 3, then we'd just say 3 out of the 5, in other words, then we would make it equals 3. And see, we would multiply these variables, W1, W2, times their contribution. Let's say the net present value they offer, or the internal rate of return they offer, or some measure that we're trying to optimize. We multiply their contribution, each one of these projects, by this binary variable. And then Solver is going to then incorporate the fact that we're going to have zeros or ones, and if there's a 1, then we incorporate their contribution. If there's a 0, we don't. And what we're trying to do is find the maximum return on whatever the particular variable is we're optimizing. So this constraint will tell Solver, okay, if I've got 1 here and 1 here, then these other 3 have to be zeros. So this does give us a great deal of flexibility in how we, in the type of problems that we can apply optimization to in business. There's also conditional and co-requisite constraints. So sometimes the acceptance of a project is conditional on the acceptance of another. And we can use a feasibility table that we see here in this slide that lists all the possible settings of the relevant binary variables and indicates which settings of these variables are feasible and which ones are not. So in this particular case, we have the warehouse project W and the P project, both zeros. This is feasible. We can choose to expand neither of them. But because the warehouse project is conditional on the plant expansion project, then if the plant expansion project is 0, which we see in the second row of this table, then if we have a 1, meaning we're going to go ahead with the plant expansion, then that is not a feasible solution. So we put a no in there. We can't expand the warehouse if the plant is not. On the other hand, we can expand the plant, but not the warehouse. But we can also expand both. So we make a feasibility table for us to see the possible combinations we're interested in. We have also the possibility of a co-requisite constraint rather than a conditional constraint that we looked on in this last slide here. So this is a conditional, this is a co-requisite. So here we can choose to do neither a plant expansion or a warehouse expansion. We cannot do a warehouse expansion if we don't have a plant expansion. But in the case of a co-requisite constraint, we cannot do a plant expansion without doing a warehouse expansion. So that's the difference between that and the conditional constraint. The conditional would let us do this third option. The co-requisite doesn't. A co-requisite means both of them have to occur. So either we get neither occurs or we get both occur. So this is how we would set up some binary variables, and then we would multiply, again, these binary variables by the factors, by the object function coefficients, and we would that would enforce the various constraints. So for the co-requisite, we just add a constraint, W equals P, so that they cannot have a 0 and a 1 or a 1 and a 0. They can both be 0 or they can both be 1. So that's how we would add in the co-requisite constraint. Okay. So that concludes the lecture on Chapter 13. Thank you.